Thank you. It's an honor to be invited, and I will talk a little bit about scars, but I'm actually switching. Patty is always awesome, and it makes my heart like flutter a little, and I have to go home and do stuff, but this is an ASLMS family. So the topic I'm going to talk about is a little lighter, regenerative medicine and lasers, and I do a lot of clinical trials. So because of my passion for scars about 20 years ago, I was like, we need a better way to fix burn patients. Cutting half their normal skin off to put skin grafts on just isn't a way. So I actually moved to Miami to be part of University of Miami to do stem cell work. But we really need new ways to replace and repair pathologic tissue. And this is not regenerative medicine, but it's hot off the press on March 21st of 21 at Mass General. This is controversial, but I think it's also very innovative. It was the world's first genetically edited pig kidney was transplanted into a human. We don't have enough organs to transplant, and there's a lot of people that die waiting for them, and this worked. They had done a very similar project in New York on a person that was on life support and going to die, and they put a pig kidney in, but I think it's pretty impressive. So regenerative medicine could be the ultimate scientific secret, and the possibility of reversing senescence, which is the condition or process of deterioration with age and loss of a cell's power of division and growth. But it's just a turn-off switch. The ability of the cell to do what it's supposed to do is still there. It's like the light is turned off. And if we can turn it back on, it may contain the most powerful healing tools that could be used in medicine to heal the body. And these tools would be in things we can't fix now. So regenerative medicine goals are really to repair and regenerate poorly functioning organs. And it's defined on a biological level. We're not talking about organs anymore. We're talking about genes and molecular events. And we want to recreate normal, youthful functioning tissue that were damaged either through disease or aging. And so I started my journey with stem cells. And stem cells are great, but the FDA does not think so. The only stem cells that are FDA approved for the use in the United States consist of blood-forming cells, and they're approved in patients that need bone marrow transplants because they're going to die, and no other uses. And the reason for this is stem cells cause cancer. Stem cells have DNA and RNA that if you have the gene for cancer, it will go to the next person. And we find out a new gene every day that causes cancer. There's a new one we found out recently for breast cancer. So induced pluripotent stem cells have not been used extensively at all, mainly because they form tumors. So what other things have been done? This is my good friend Tony Atola. And Tony's at Wake Forest, and he and I work a lot together in the military. And he has developed a stem cell bladder, and he has put it in patients, and it functions. And he did it with an inkjet printer, which is super cool. So I think we will have more of these things coming in the future, where you can do 3D printing of anything. It's very like the Ocean's 8 movie where they did the necklaces, right? You know what I'm talking about? Yeah. So you can 3D print anything. So one of the things that I have done in the past is I wanted to use laser-assisted delivery of stem cells. I thought this will fix scars. So that's my team at University of Miami. We go into a little basement. It's super glamorous, and we laser pigs and rats. So we wanted to see if laser-assisted delivery, which we use a lot for scars, and we put things down those channels to help with scars. I wanted to see if we could put stem cells down those channels. And the first thing we looked at was which laser. Is it the CO2 or erbium? The same. We can talk more about that, but I've done about 10,000 experiments over about 15 years. Then we wanted to look at different stem cells. Were the fat stem cells the best? Were allogenic, which means from another pig, or autologous from the same pig most effective? The answer there is allogeneic. Another pig's stem cells did the best. And then we wanted to look at different ways to occlude the stem cells to make sure they worked. So in our studies of the pig, we took our cute little pigs, and we unfortunately we're very humane, and there's a lot of regulations, but the pigs are asleep, and we have a burn degree model, and Professor Davis at University of Miami did this. I think we're the only people in the world that have an actual third-degree burn model. And then I lasered it with either CO2 or erbium, and then, this is super cool, we topically applied stem cells, like half cc. Now, on one side of this little cute pig, we used laser CO2 and stem cells, or erbium and stem cells, and pigs are really big. And on the other side, we just did laser alone, and that's going to be important in a minute. So we saw pretty cool things within a few days. The one on the left is our stem cells. We saw the reedy ridges reappearing, and what was really interesting is the dermis formed first, and its reedy ridges, then the epidermis formed over it. I always sort of thought it was the opposite. I thought the epidermis would heal first, and then, but it wasn't that way. And then on the right is scar. That was control. So that was pretty cool. And so the fractional laser, actually, you could see the laser channels, and the stem cells sort of grew down into where the laser channels were, recapitulating skin. And a lot of times in our scar skin, it's very fragile because it doesn't have this interlocking mechanism, and it just very easily will get injured. So that was super cool, and we were excited. Now, Dr. Badiavis said, let's fluoresce these cells. So that's a CO2 or erbium channel. And those are our stem cells from another pig that stayed around that channel for up to 30 days, and they were alive, and they were actually dividing, so they were good. And we thought, well, that's really cool. We delivered these stem cells, and they stayed right where we put them. And then that's another, I think that's a cool picture of more fluorescent stem cells that are marked. Now, then the bad news one day is I got a call from Lewis in the lab, and he said, Dr. Weibel, the control side. Remember when I said we flipped the pig over? So it's like the front of me, the back of me. The flip side of the pig, they're like, there's a stem cell. And the stem cells were put on the whole other side of the pig. So what that meant is the stem cells went all the way through the blood supply and came out the other side. Yeah, that's a big whoa. Which also, when we did this in mice, we sacrificed the mice, there were stem cells in every organ. So I think this was a good learning lesson. When we use laser-assisted delivery, which I'm a huge proponent of, it's going everywhere. You know, there's blood vessels, these things travel, you're not necessarily just localized. So there's a little picture of some stem cells of ours going through blood vessels. So the next thing we did is said, well, let's see if they're in every organ, including the brain, by the way, when we sacrificed the pig or the mouse. Do they work? You know, are they just floating around? Are they doing something? So we have this little mouse. He's a skid mouse, and he has like a leukemia. A skid mouse has no immune system. And we gave him a lethal dose of radiation. So he is unfortunately going to die. Then we took an erbium laser, and we put one laser pulse, about 20 micrometers, again, thin skin, and we took little green mouse, he's a healthy mouse, and we took a little bone marrow out of him, and we topically applied a little bone marrow on top of our little erbium laser. And every mouse that got like a drop of this guy's stem cells lived, and every mouse that didn't died. So we basically cured leukemia using laser-assisted delivery of stem cells in our little mice. And we published this, and I mean, I thought that was very powerful. And the fact that we can do this is pretty amazing. Again, we can't do it because we can also deliver genes for cancer, but we basically did a bone marrow transplant and cured leukemia, and we could prove that there was the engraftment of the donor cells, and that we could prove the DNA was actually functioning in the donor mouse. So that was kind of cool. Now, what has happened to human studies? Well, despite regenerative medicine being the talk of the town for the last 30 years, its performance at bedside has been very disappointing. And why is that? It's because it's very disruptive. It's because there's a lot of challenges. The biggest one is safety and FDA regulation. And the FDA is right. I am 100% behind the FDA. So the only frontier left for stem cells is one more shot, and it's amnion-derived stem cells because they do not form tumors. So unlike bone marrow, fat cells, they can be differentiated into all three germ layers. And I think there was one one abstract on umbilical line stem cells. So umbilical line stem cells could be our last hope. And there's a couple companies that I work with in both, and one of them is where Tom Brady, very hot, gets his stem cells. None of these clinics are in the United States. There's one in Mexico. There's one in the Caribbean. But there's a chance we will hear back from stem cells. But for right now, stem cells, we learned a lot, but they've been tabled. So if we can't use stem cells, can we use exosomes or maybe mRNA? So exosomes are getting a lot of bandwidth right now, but I'm going to put on my Patty Owens compliance hat right now, which is important. I do not use exosomes. Exosomes are super cool. I also believe in them. They have a lot of things that they excrete, and they do wound healing and repair, and they talk to each other. They're what we spit out of ourselves to communicate. And they can have a major impact in our field of aging and photoaging. Now, if you look at this article in Science Advances, it says small extracellular vesicles from young adipose-derived stem cells prevented frailty, improved health span, and decreased age in old mice. So there's some cool studies going on out there. Now, my question is always, what's more important, the soup or the poop? So the stem cells are the soup, right? They're what are really directing the activities of our life. The exosomes are these extracellular vesicles, which we all learned about in school, that were really first described in 1983. And again, they carry information, they talk to each other, but here's the big one. They transmit disease states. We think this is where most of our rheumatology, most of our autoimmune diseases, and they usually have proteins, mRNA, and DNA in them. So do you hear a common theme? What happened with our stem cells? Now, our exosomes have mRNA, DNA in them. So the good news, again, is they have some really good things going on, but the bad news is they have some really, really bad things going on, like tumorigenesis, angiogenesis, and metastasis. But exosomes come from different sources. So if we put a rose plant exosome in our body, is it okay? We don't know. But it sounds better than putting, a adipose human stem cell or exosome in our body. There's platelet-derived, there's neonatal, there's bone marrow. But the big answer here is we don't know. Now, here's one for you. I will not tell you who I was talking to. I was talking to a company that I've used their skincare product for many years. And they're like, we think there's exosomes in our skincare products. So even though we're kind of making a big fuss of exosomes really work great, and then I'm making a big fuss of, and FDA is exosomes probably aren't safe, we probably have exosomes in 90% of things we've been using forever. So, and it'll take us years to figure this out, by the way. So, we're learning a lot. There's very little understanding. There's very few experts in this area, but cell origin matters. Your target cell matters. The extravascular size matters, and your concentration matters. So again, pros, I think there's some great things that exosomes are going to do. Anti-inflammatory, collagen, melanin, skin aging, and tissue repair. The cons are big, though. Immunogenicity, biodistribution, tumorigenicity. There's a lot of regulatory standards and controls. Now, the FDA is our friend, and I went to both the FDA sessions, and they will tell us that as clinicians, this is the practice of medicine, and we are allowed to try something that we believe will work. After we try it 1 or 2 times, then we must do studies and go through the process. But on 8/10/2023, I had a company call and said, hey, we want you to do a clinical trial on skincare, which has exosomes in it. And I said, well, I'm on the Aesthetic Stem Cell Committee Board of Directors. I'm a founding member. I go to the CBER all the time. I talk to Dr. Marks, and this doesn't sound good. So I sent an email to my friends at CBER and said, hey, can I do this clinical trial on skincare, topical application of exosomes? And they basically said no. They said exosomes are regulated by CBER, and at this point in time, FDA has not approved exosome for any use at any time. Now, just because people use this, they say, well, it's a cosmeceutical, you don't have to go through the FDA. That is true if it is a cosmeceutical, but if it has a biologically active material in it, it is not a cosmeceutical, it is a biologic. So it really makes me sad as I get older. Every person that uses these is, if you're a clinician, you're responsible to know the FDA rules. You can't just turn a blind cheek and say, I'm going to use this because company A said it was okay. Also remember, the FDA does not have a regulatory arm. They've gotten a little saucy lately, though. They send things to the Justice Committee and so forth, so they also, not only did the FDA tell me this, they also said, by the way, we've put out a consumer alert on things, including exosomes, and you can actually complain if you're using one of these products. So that's a lot. I mean, the FDA usually is pretty passive. So anyway, but there are 165 exosome trials, so that's good. So we're studying them. Again, I'm pro exosome, but I'm very pro safety. There's also a position statement. This was an international position statement. I am not part of this, but the International Society for Extracellular Vesicles, they also believe that we still have a lot to learn, that some of the exosomes might have contaminations, heterogeneous preparations, and we need to look more into this. So I think it will come. Now, the next thing I want to talk about is we're doing a lot of fun things in aesthetic and laser medicine, but do we really understand what we're doing? And because we've moved so quickly in regenerative medicine, I think we now have to have an understanding of the molecular, cellular, and tissue level of the treatments we're doing. And we can use genetic biomarkers to see what, like aging, but we can also look and see what an outcome does on aging. And it's one of my goals to systematically look at a bunch of different outcomes to determine what we're doing to tissue. So this I've reported on a couple times at this meeting. I wanted to look at what are the gene pathways. I really wanted to look at it in scars, but Galderma sponsored this and they made me do it on label, but it's the same thing that's going on in scars because it's the same device, and this is considered a device. So what genes are being stimulated when we inject calcium hydroxyapatite and polylactic acid? So this was a scar patient of mine in 2009. I rubbed on topical PLLA after the erbium laser, and voila, boom. One treatment. I'm like, wow, this is amazing. And I think this is the most amazing scar thing we can do, is to use laser plus PLLA. And I went on to do I did all the clinical patients. These are all one treatment session. And then my good friend, Dr. Ozog, used a cadaver to show that the PLLA goes down these channels. So we know it works clinically, which is very good. We know that it goes down the channels, so we can actually, and I know I can't get in one treatment this result with laser only or PLLA only. So that combination is pretty powerful. Dr. Geronimus did a safety study showing that, we don't have nodules. So I feel really good about PLLA. But what I don't know is the mechanism of action. So we did punch biopsies, and we looked at 107 genes, and I'm going to catch up time. You can read the article, but what we found was that PLLA stimulated the regenerative pathways, and it was the fat that it stimulated. We think of these as collagen stimulators, but it's really the fat progenitor stem cells stimulated everything else. The CAHA, and I'm not anti-CAHA, but it was a much more inflammatory pathway, and that's okay. Inflammation leads to collagen too. But when we really looked at the genes, the PLLA did the extracellular matrix, and I didn't put it in this study, but it also, that when we then took the genes and we put it into this free database called String Analysis, and we looked at what protein pathways with all the genes that were turned on over 50%. It took for many months. But long story short, we could prove that PLLA, the genes that were turned on, stimulated protein pathways for collagen, elastin, and see that DKK1 that Alan Whittaker called me and, hey, there's this aberrant pathway for pigment. I'm like, no. PLLA stimulates pigment. I see it all the time. So that was pretty fun. So anyway, now we sort of have an understanding of what PLLA does, what CAHA does, and it's good. So then I did a study on gene pathways looking at microcoring, and I had patients with microcoring that were amazing. This is my best ever. This is one treatment 1 month later. Like, I was trying to get the green tattoo ink out of her lips, by the way. I wasn't even trying to do all this laxity work, but my nurses were like, oh, do your neck too. But then sometimes you have patients, it's better, but it's a little bit better. So a lot of variability with my patients. So we took the cores out of the patient, and we looked at the genes at day 0, 45, and 90. And this was painful. We had to wipe all those little cores out and put them on that little surgical towel and fill up a little beaker. Although someone yesterday said we should start doing all skin biopsies this way. It's kind of a good idea. So cutting to the chase, the first thing to know is that for all the genes, and these are the collagens and the elastin, the most important, 0 is baseline, day 45 is the green, and day 90 is the orange. First takeaway message is it takes time to build collagen and elastin. And I tell my patients that in the clinic every day. It takes 3 to 6 months. So at 45 days, things are going up, but not much is happening. But at 90 days, things were very up. And this is just one of those gene markers. This is collagen 3A1, which is probably the most important collagen we have in our body. At day 45, patients had anywhere from a 31% to a 412% increase in the genes that make collagen 3. That's amazing. Clinically significant is 1.5% from 0 is baseline, and this is an increase. At day 90, Look at patient 7, 656% collagen increase. Now I want to go back and look at the fractional lasers. I'm looking at you, Sonia, and do a study on the erbium and the CO2 and then compare it to this so we can start understanding what we're really doing when we're treating our patients. So that's exciting. And then the last two things I'm going to finish off with is I've been doing work with Dr. McDaniels and Dr. Charles Boyd and Joe Lewis with the oxalotl salamander. He's the most regenerative animal in the world. You can cut off his leg 100 times, take out his heart, take out his brain, he grows back. So we finally figured out what we think is the magic sauce that causes him to regenerate. Again, we have a lot of genes. We've done a lot of experiments. I took this to the lab at University of Miami on the burn unit with 8 applications, and within 7 days, one of the applications had healed the burn wound within 92%. I've been doing these burns for years, and it usually takes 3 weeks. So we're very excited about our little oxalotl. And then my red light is blinking, and we're already late. So the last thing is, there's a gentleman at Stanford, his name is Dr. Vittorio, and he took Dr. Yamanaka. Dr. Yamanaka figured out how to do induced pluripotent stem cells so we could use them in the lab, but they cause cancer. So Dr. Sebastione has figured out how to take a cell backwards in time. So a 70-year-old cells can now act like a 20-year-old cells, but they don't go back all the way so they don't induce cancer. So it's very exciting. It's an mRNA model. And the older you are, the younger your skin gets. So this is all in the lab. There's nothing in the human, but we're going to be doing human trials soon. So with that, I will end, and thank you for having me.